Have you ever wondered how the tires of the colossal Airbus A380, the largest commercial airplane in the world, can support its immense weight during an extreme landing? Crafting these tires involves a meticulous process that combines engineering precision with advanced material science. The Airbus A380, with a maximum takeoff weight of 1.2 million pounds and a landing weight of 862,000 pounds, can cover a range of 7,700 miles. Yet, its tires endure landings at speeds approaching 170 miles per hour. The force on each tire during touchdown can exceed a mind-boggling 38 tons. But how are these remarkable tires made in the first place? You see, airplane tires are designed to handle the tremendous weight of aircraft through a combination of advanced materials and engineering. They are typically made from multiple layers of specialized rubber compounds, reinforced with strong synthetic materials like nylon and Kevlar. These materials provide the necessary strength and flexibility to support the weight of the aircraft during landing and takeoff, as well as while taxiing on the runway. Interestingly, the cost of airplane tires can vary significantly depending on the type of aircraft and the specific tire model. On average, a single airplane tire can cost anywhere from $2,000 to $5,000 or more. Moreover, the tires are designed to be highly durable and capable of enduring numerous landings and takeoffs without significant wear. On average, they can last between 200 and 300 landings, depending on various factors such as runway conditions, aircraft weight, and maintenance practices. For commercial planes, which typically use multiple tires, often 6 to 10 or more depending on the aircraft type, this durability ensures reliable performance over extended periods. For those big commercial jets like the Boeing 747 or Airbus A380, you're talking multiple tires, like 6 to 10 for smaller ones and up to a whopping 16 or more for those mammoth wide-body jets. It's all about ensuring safety and performance, mile after mile in the sky. So, now that we have seen what makes airplane tires so robust and essential, let us look more closely at the detailed process by which such key components are fabricated. Step 1. Design and material selection. The development of airplane tires starts with a clear understanding of the aircraft's requirements and the diverse, challenging environments the vehicle will encounter. It begins with analyses of data from earlier designs of the tires and operational feedback. This will include information on the maximum takeoff weight of an aircraft, landing speeds, runway conditions, from icy tarmacs to scorching desert asphalt, and even climate variations across global routes. Every one of those parameters, from the size and shape to the kinds of compounds and reinforcements, defines this tire design. State-of-the-art computer modeling and simulations come to the fore after initial specifications are set. Simulations can be used to test virtual configurations under a variety of stress scenarios. Think of a digital tire spinning through innumerable landings and takeoffs, and evaluating how it cools itself when things get hot during braking or handling forces at touchdown. This kind of digital testing not only fine-tunes tire performance, but also guarantees that it will meet the very strict guidelines on safety prescribed by aviation authorities. But that's not the end of it. Real-world validation is key, and engineers introduce physical testing onto prototype tires by pushing them to the extreme in controlled environments. They measure everything from tread wear patterns down to the capacity of the tire to hold its form at higher speeds. This hands-on testing phase yields a feedback period vital for fine-tuning the design before production ramps up. Step 2. Rubber compounding. The rubber compound will be the lifeblood of an aircraft tire, as this dictates its traction with the runway, resistance to high or low temperatures, and wear. The process of creating these compounds calls for a fine balance between science and precision engineering. First, the production process begins with the choice of appropriate base materials, synthetic rubbers which can give the required properties, for example, elasticity and thermal resistance. Base materials are mixed with other elements and additives, which include carbon black, silica, and chemical accelerators. Carbon black enhances the strength and durability so that it is reliably used for rubber applications such as treads. Silica gives a good grip on wet surfaces to ensure a safe landing in the rainy season. Creating the perfect rubber compound, however, is only half the battle. Good compounding is all about consistency and repeatability. Advanced mixing techniques are employed by engineers in order to ensure homogeneous dispersion of additives in the rubber matrix. Having uniformity is essential because the performance and life of the tire depend directly upon it. Mixing is followed by rigorous testing of the compound. The samples undergo physical tests to determine the tensile strength, elongation, abrasion resistance, and other properties. Quality standards in relation to the compound are very sharply defined, with no defective materials that may impair performance, which is ensured through chemical analysis. Step 3. Fabric and steel reinforcement. When it comes to airplane tires, strength isn't just an option, it's a requirement. That's where fabric and steel reinforcement step in. Inside each tire, layers of high-strength fabric are strategically embedded. These fabrics, often made from materials like nylon or polyester, act as the tire's skeleton, providing crucial support and structure. But wait, there's more. To handle the intense forces of landing and takeoff, high-tensile steel cords are intertwined within these layers. These steel cords are like the hidden muscles, adding resilience and preventing the tire from deforming under pressure. Now, here's the magic. These layers of fabric and steel are precisely positioned to ensure uniform strength and durability across the entire tire. It's a carefully choreographed dance of materials, each playing its part to perfection. This reinforcement not only enhances the tire's ability to carry heavy loads, but also improves its resistance to wear and tear, extending its lifespan and reliability. Step 4. Building and curing. This process kicks off with the assembly of the tire components on a drum-shaped mold. It's like building a layered cake, but instead of frosting and sponge, we're talking layers of specialized rubber, fabric, and steel belts. Each layer is placed and compacted under controlled conditions, ensuring optimal strength and flexibility. But here's where things get interesting. The assembled tire undergoes a transformative journey inside an autoclave. What's an autoclave, you ask? Well, picture a massive high-pressure oven. Inside this pressure vessel, the tire undergoes curing, a process where heat and pressure work their magic. The rubber compounds bond together, forming a resilient matrix that can withstand the extreme temperatures and pressures encountered during flight operations. During curing, precise temperature and pressure profiles are maintained to ensure uniformity and integrity throughout the tire. It's like giving the tire its final stamp of approval, ensuring it meets rigorous safety standards and performance criteria. Once cured, the tire emerges stronger, more resilient, and ready to tackle the challenges of aviation with confidence. This meticulous process of building and curing isn't just about making tires, it's about crafting reliability, safety, and performance. Step 5. Inspection and quality control. Once the components of an airplane tire are assembled, they undergo a rigorous inspection and quality control process to ensure they meet the exacting standards required for aviation safety. This phase is critical, as any flaw or inconsistency could compromise the tire's performance during flight operations. Imagine a tire being scrutinized with the precision of a surgeon. Advanced X-ray technology is employed to inspect the internal structure of the tire, checking for any hidden defects or imperfections in the layers of rubber, fabric, and steel. This thorough examination ensures that the tire's structural integrity is uncompromised and capable of withstanding the immense pressures and forces experienced during takeoff, landing, and taxiing. But inspection doesn't stop at visual checks. Dynamic testing takes the tire's resilience to the next level, simulating the stresses it will endure in real-world scenarios. Each tire is mounted on specialized test rigs and subjected to extreme conditions. It's spun at high speeds, exposed to varying temperatures, and tested under heavy loads. Engineers meticulously monitor how the tire performs under these circumstances. measuring its ability to maintain shape, grip the runway, and dissipate heat effectively. Only tires that pass these stringent tests earn aviation certification. Each tire is marked with detailed specifications, load capacity, maximum inflation pressures, speed ratings, and other critical data essential for aircraft operations. Pilots and maintenance crews rely on these specifications to ensure that every tire installed on an aircraft is capable of performing its crucial role safely and efficiently. Step 6. Final testing and certification. After passing inspection and receiving certification, airplane tires undergo final testing to verify their performance in practical aviation conditions. This stage is where the tire proves its readiness for the demanding challenges of flight. The tire is put on a test rig, bearing weight equivalent to that of a fully loaded aircraft. It undergoes a series of tests to assess its load capacity and durability. Engineers monitor how the tire handles the stress, ensuring it maintains shape and structural integrity without any signs of deformation or failure. In aviation, heat resistance is crucial. The tire is subjected to intense heat cycles, simulating repeated landings and takeoffs. This testing ensures that the rubber compounds can withstand high temperatures without softening or degrading, maintaining optimal performance throughout its operational life. Engineers measure its braking performance, ensuring it grips the runway effectively without slipping or skidding. This capability is essential for safe landings and emergency braking situations, providing pilots with confidence in the tire's ability to stop the aircraft securely. Once all tests are completed successfully, the tire receives the green light for flight. It's certified as airworthy, meeting all regulatory requirements and safety standards. This certification marks the culmination of a meticulous manufacturing process, where precision engineering and rigorous testing ensuring that every airplane tire is ready to perform its vital role in aviation safety. So, the next time you board a plane, remember the tires beneath the wings, crafted to ensure a smooth journey through the skies.